Another force that we want to learn about in chapter 6 is the force of air drag. And this is the first case that's come up in this class where we have a force that depends itself on the speed that something is moving. So air drag is kind of like friction, but it's also kind of not. It is a frictional force. It's resistance, but in this case, it's of an object moving through a continuous medium of fluid. Um, there are actually two forms of air drag for relatively high speeds of, say, for example, your car moving through the air. You have a kind of air drag that is quadratic in the speed. So it's a turbulent air drag. And that's the one that we're going to learn about. But you should also keep in mind that there is also for low speeds Stokes drag, which is linear in the speed. And so for like little bugs moving through the air, they wind up in the Stokes regime. So just somewhere in the back of your mind, going forward in physics, try to remember that there are two different formulations and two different regimes depending upon how fast the relative motion of the object through the fluid is. But for now, we're going to deal with turbulent drag. So D is the drag force. It depends on quantities as follows. So a half, obviously a constant. Capital C is the drag coefficient. So for a given object and shape of an object going through a different kind of fluid, you're going to have a different drag coefficient. And so these are tabulated. Not something that we would worry about measuring empirically or calculating from first principles in this class. We'll just take it as something that you can look up a value for when you need to apply it. Rho is the mass density of the fluid, so density per unit volume. A is the cross-sectional area, and V is the speed, and it's turbulent drag, so it goes as the speed squared. All right, so drag force is constant half, constant drag coefficient, density of the fluid. So the more dense the fluid, the greater the drag force, which that would make sense. The greater the cross-sectional area, the greater the drag force. So if you are going out of an airplane and you want to slow down as much as you can, you're going to spread yourself out star-shaped as big as possible. You want to have as big a cross-sectional area as possible. And instead, if you want to fall faster, then you're going to put yourself like a needle, try to give yourself the smallest cross-sectional area. And then the faster you're going, the bigger the drag force gets, which that brings up the idea of a terminal speed. Terminal speed is when the drag force is just as big as the weight of an object. So for our following cat over here, there's the drag force going up, and then the force of gravity going down. And when those two forces are equal to each other, so the speed has gotten great enough that the drag force cancels out the weight, then you're in the regime of Newton's first law of motion. There is no net force, so you move at a constant velocity. And so once you're going fast enough that the drag force is as big as the weight, then you're at your terminal speed. You're not going to speed up anymore. Drag force isn't going to get any bigger, and obviously your weight isn't changing. So to find the terminal speed, we just set the drag force equal to the weight. We have a subscript t on the speed term to show that it's the terminal speed. We'll just rearrange that equation, get the terminal speed on one side, and you have twice the weight for the drag coefficient, density of fluid, cross-sectional area again, all under the radical. All right. We will do more with fluids later in the class. but wanted to introduce at least the idea of air drag to the point of a terminal speed at this point. And we'll learn a bit more about fluids later on. All right, let's do a question. We have a feather and a minivan are dropped vertically from a height of 20 meters. Both are subject to air drag as they fall. So this is not free fall for either object. The minivan reaches the ground much faster than the feather. Probably what you expected, but why? Which of the following statements concerning the situation is true, if any? So read through those all, see which one makes sense, talk it over with your physics friend, and then you can unpause the video and we'll go over the answer. All right. So our answer is E. Ka-ching. Now let's talk about why. So the minivan has a larger terminal velocity than the feather because it experiences less air resistance than the feather, which is not true. The air drag force is going to be way bigger on the minivan in terms of like a force in newtons. So that's not true. Let's look at B. The minivan encounters a smaller force of air resistance than the feather and falls faster. No. Again, the force of air resistance as measured out in newtons on the minivan is going to be huge. Each object experiences the same amount of air drag. No. But the minivan experiences the greater force of gravity. Well, that's true, but first part of that sentence is incorrect. D, the feather experiences more air drag than the minivan and has a smaller terminal speed or terminal velocity. Again, not true. The feather does not experience more air drag. The force of air drag is bigger on the minivan. And so none of those statements are true. What is happening is the feather almost immediately is going to reach its terminal speed, and then it travels at a relatively slow terminal speed and floats down to the ground. The minivan, to get a force of air drag that cancels out its weight, would have to fall a tremendous distance to get there, to moving that fast. And its terminal speed is just higher. So it is going to reach the ground faster. All right.